Now let us see how we represent numbers in binary. Now let us take an example of a number and let's see how we evaluate such a number. Now let us suppose the number is this. So how do we evaluate the value of this number? So you multiply every bit, every digit of this number with an equivalent of 2 to power some number, some value. So how do we do this? So this will come out to be multiply the first position with 2 to power 0, second multiply this by 2 to power 1, and with every subsequent bit you need to increase this power. So this goes from 0, 1, 2, 3, 4, 5, 6, 7. So the last bit will be multiplied by 2 to power 7. So the only bit that will hold significance will be those that are ones. Rest all zeros will subsequently go to 0. So only those that will be contributing to the value will be those which are represented by 1. So we have 1 into 2 to power 0, which will be 1. We have 2 to power 1, which is 0, 2 to power 2, which is 0. So we have 2 to power 3, which is 0. So let us write down only those which have impact on the value, which is 2 to power 4. Then we have 2 to power 5. So let's see what actual value this comes out to be. So this is 1 plus 2 into 2, 4, to 8 to 16. So we need to add 1 plus 16 plus 32. So the number comes out to be 49. Now how do we know whether this number is positive or negative? Now this is the extreme left bit, which actually tells us what exactly is a number. If the extreme left bit is 0, the number is positive, and we can write on a plus here. And in case the extreme left bit is 1, the number is negative. So in case we have 1 here, so this is not the process that we'll use to calculate the value. We'll shortly see how do we calculate the magnitude of negative numbers. As of now, the 0 in this position says the number is positive, 1 in this position says the number is negative. So this is how you can evaluate a binary number to its decimal equivalent. Just multiply every bit with the corresponding value in 2 to the power position minus 1. So in case this is the first digit, it will be 2 to power position minus 1. So multiply every bit with this value and then you add all those that you obtain. So the total will give you the magnitude of the number. Now let us see the reverse process, where you have a number and you want to create the binary for this. So suppose I have a number, say 20, and I need to see what is the binary equivalent for this number. Now I've just created a dummy for this, all zeros, and we'll replace a 0 with a 1 where we need to make a change. So how do we decide where we need a 1 and where we need a 0? So 20, if we just make a sum of, if we just cut down its factors which are multiples of 2, then we can see we have 16 plus 4. So these are the factors for 20 that are multiples of 2. Now this stands for 2 to power 0, this is 2 to power 1, this is 2 to power 2. 2 to power 2 goes to 4. So replace this with a 1. Then we have 16. This is 8, this is 16. So you have 0 0 0 1 0 1 0 0. So this is how you convert a number to a binary equivalent. So let's see another example so as to get this better. Now let us see an example which is now 35. So let us again follow the same process. Break this into multiples of 2. So if I can just see what it can be. So this is one. Now let us see 1. 1 will put on a 1 here because 2 to power 0 goes to 1. Then we need a 1 in for 2. Here it is. Then we need a 1 for 32. So this is 2, 4, 8, 16, 32. So we need a 1 here. So the representation for 35 will be 0, 1, 0, 0, 0, 1, 1. So this is how you can convert any number to its binary equivalent by just breaking down into factors which are multiples of 2 and whatever is left our number say 1. So this value will always be 1 and rest are all multiples of 2. So you can accordingly put on 1 in position that corresponds to the corresponding factor.